Recording in progress.
That's too many buttons.
No.
You think this is good?
Everyone, you guys hear me? Yep. All right. Great. Thank you.
I can hear you.
All right.
Yep.
Thanks. Thank you. All right. So we're gonna get started. A few people are still coming in, so please mute your microphones if you haven't done so already. Yeah. So we're gonna get started. So as you know, we are running remotely today because of the weather situation. So that's fine. I'll be recording this session also and posting it later. All right, so I'm sure some people will still come in and interrupt, but that's fine. We'll get started. All right, so we're currently on week 3. So this is week 3 of Machine Learning Foundations. Today's lecture, and then we have, another on Wednesday. So let's go over the material for this week. I'll be moving this around. So you have a homework assignment that's due on Wednesday, so make sure that you're working on that and to submit it. This week, we are going to focus on these 3 modules here in the sequence. As you can see, the machine learning pipeline, KNN, unsupervised learning, and K-means. So this is several different algorithms. So today, this week, we're starting now with algorithms, and we're going to start with a concept called the vector space model also. So this is based on like geometry, and so it's pretty intuitive, I would think. I do have some slides, so I'll cover the slides first, and then I have some code examples that we can discuss. I put together KNN and K-means because they're essentially the same environment medium, and the only difference is really they're 2 algorithms, in fact. So they're different algorithms for sure, but they're very similar in how they attack the problem. So these would be more classical or traditional machine learning algorithms and not neural networks. All right, so I haven't really covered neural networks yet until like after the first exam probably. So we are just going over these algorithms. So let's start. So here you can see the sequences today. I have a slide here that I like to cover, the machine learning pipeline. So now you had some experience going through Weka, which made things easier. Everything from now on, because we're going to we're going to have to use more powerful tools, will require using coding, more powerful libraries. We'll be using Colab and GPUs as well. And then we'll get into KNN. So let's start here with the machine learning pipeline. And we talked about feature engineering already with the problem definition, the word problems. So let's take a look. This is just a PDF that I have available. Yeah, so all right, anyway. So let me move this over here. Correction. Sorry, I'm trying to figure out where to put this. Okay, that might work. All right, so let's take a look at the machine learning pipeline. And I put together this like slide of what machine learning is. This includes a lot of the topics that we're going to be covering this semester. And really, it's just a sequence of the steps, right, that we have to follow. So you can see it's a sequence that goes in that direction. ML pipeline. So let's just kind of start here. So the first thing we do is to identify a problem, such as a word problem, right? So we want to do network security of some kind. Okay, then you have to identify what the goal is, maybe to detect intrusion, what the data is going to look like. So network packets, as we discussed in a previous lecture. And so that's the idea. So you identify the problem. And if you remember, from the word problem, so we follow this orange line, we know that what we're trying to do is take the data and put it in a very specific format, the X matrix and the Y vector. If we do that, if we always think in terms of creating that X and Y matrix and vector, we always have a plan on how to approach so that we can convert any problem into a machine learning problem. A few students coming in. All right, once you identify the problem, then you have to figure out if you have the data or you need to collect the data. So usually so far we've been getting like files of data, right, that we downloaded, so the data was already ready to go. But as you start to look at problems, in your environment, etc., you're not going to have the data, so you have to collect it. So what are the sources? So obviously social media has a lot of data, like text is, tweets and things like that, images. There's also these things called web crawlers, which are essentially searching across the internet and downloading, scraping essentially HTML and the text. So that's a web crawler, getting links, the scraping, getting the data. Images, you can take pictures of things. But there's also other things like sensors that can collect a lot of data. If you have like an industrial plant or something like that, so that's also, something that can happen. All right, so collecting the data, the next step is to do feature engineering. Usually the best way to think about representing your data is to think of feature engineering. So you want to identify what a sample is and what are the features that represent each sample. So for instance, we have a packet that's a sample, and then we extract values from the individual headers. This is going to be the vector space model. So as you can see, we have a X, Y, Z axis, but we can have more axes as well in higher dimensional spaces. So this is actually the best way to think of representing your data. It's a very nice way of thinking about it, and by putting your data in that format, you can then use many of the machine learning algorithms. So today, once we get into KNN, KNN is going to assume that we're using a vector space model, so this is something that we want to look at. Once we think of the feature in feature engineering, then we talk about pre-processing. So we're going to think about, do we have labels or not? Do we one-hot encode the data? How do we clean the data? What are the transformations that we can apply to the data, etc. So there's, like a process of just cleaning the data, making the format more friendly, etc. Scaling is going to be, notice that I wrote important here. This is a step that you should always consider, which essentially has to do with the fact that different features, that is, different columns in your data set, might have different scales. So for instance, if I'm looking at housing prices, it might always go from $50,000 to $300,000. That's the scale. But if I'm talking about age, it's going to go from 0 to 110, right? So you can see one goes from 0 to 110, one goes from 0 to 300,000. So the scales are very different. And what you want to do is you want to rescale them proportionately so that they go from 0 to 1, both of them, in relative terms. And so these techniques are going to be called scaling, and we will be applying them. And you will see that these techniques do help out a lot in machine learning. You really just don't want the feature that has the highest range, like the housing price, to dominate over another feature that has a smaller range but may be more important. So this is critical. Then, as you can see, you've already done a little bit of this feature ranking, right? So you did that in Weka, and that's just to see the importance of the features. We have 1,000 features, and we want to see which ones are important, and maybe we can drop a few. Additionally, there's going to be a concept called dimensionality reduction, which we will cover likely this week through a technique called singular value decomposition. There's also PCA. We may not get into the algorithms of these two techniques today, but at least I will start using them, and you will see this is another technique so that imagine we have these 1,000 features. One approach in feature ranking, we rank them by importance and drop the 300 least important features, and we get rid of them. So the problem with that, obviously, is that we are losing some information. Another technique is dimensionality reduction, like PCA or SVD. What they do is they take the same 1,000 features and they transform those into 700 features, right? And it's like we compress them, essentially. So there's an algorithm that allows you to do that, and the idea being that some of the information from the 300 that may have been important is not just thrown away. It is just like sprinkled on the other ones, if you want to think of it that way, so that we retain it. But they both achieve similar objectives. Obviously, SVD and PCA do have other applications which are also really important, like for recommender systems, things like that, collaborative filtering. We'll talk about that later in the semester. All right, so these, as you can see, are the steps that you want to apply. And then finally, hopefully after you've done all these steps, the data set is ready for machine learning, which means it is X and Y, right? And this is what we have seen in the previous 2 weeks of the semester. We just had our iris data set or our bicycles data set, and they were all ready to go into Weka. So that essentially is what happens here. We have, think about all the steps, right, that went by before what we've been doing since in the last 2 weeks. So, in those we already had X and Y defined as files, but there's a lot of things that had to be done to create that file, iris.csv. Once we have that, the data set is ready in the format, what we can call a CSV. It's in the vector space model. We know we've got rows, columns for the X matrix. We know we got rows and columns for the Y vector. Once we have our X and Y, then we are ready to select our machine learning algorithm, if you notice here. And there are many, many options, as you have already played with. Using Weka, you've been able to select one algorithm over another algorithm, and you're able to evaluate performance. So this week we'll cover KNN. You've already used KNN when you use the IBK algorithm for the WECA assignment in the demos, right? So we've already used the algorithm, but now you get to understand and try to implement how this algorithm actually works. So we'll try to implement it in Python. Other algorithms that we can discuss later in naive Bayes, perceptron, neural networks, deep learning, linear regression, logistic regression. So these are algorithms that we can cover. K-means also is an algorithm that we will cover this week. And then there are other ideas that we might cover later in the semester, like reinforcement learning, hidden Markov models, Gaussian models. And so these are also, other kinds of techniques that we can. So there are many options, and some of them depend on the type of problem that's being tackled. Okay. I think somebody. Okay, yeah. Yeah, thank you. I already posted the initial course participation. All right, so. All right. And then once we have the algorithm, as you guys know, we have to kind of think about the labels, right? We've talked about this in WECA. Is it numeric or nominal? So is it labels or is it no labels? And hopefully this week we will see the difference between supervised and unsupervised. That's kind of one of the big concepts to explore. KNN algorithm will be for supervised learning. K-means will be for unsupervised learning. So I will talk about both of those. So you know, of course, that we can have real valued number, and remember this is important, we call those regression problems, or when we're just trying to predict one of a set of discrete values like classes, and that's, classification. We also have in machine learning things like sequences, so that might be something that we look at, especially with hidden Markov models. How do you look at the prediction of ice cream given that the temperature, is the information we have? So for instance, I want to know the consumption of ice cream this week, Monday, Tuesday, Wednesday, and Thursday, and Friday, just by looking at the temperature. So snowy today, cold, 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 but maybe on Friday, all of a sudden it gets much warmer. So from there we can infer that no ice cream Monday, Tuesday, Wednesday, and Thursday, but by Friday the likelihood of ice cream goes up. And so we'll look at techniques such as that one. And then finally, which is key in machine learning, as you can see in this little box, is going to be our performance evaluation. Okay, so performance evaluation here. And you've done this already with WECA. That's the beauty of WECA, right? You run the algorithm, and then it gives you that thing we call the confusion matrix. And I've talked about how precision, recall, F measure for classification come from there. For the regression problems, we had the correlation coefficient and root mean squared error. So you can see these are some of the metrics. And I've mentioned to you, when we have imbalanced data sets, you really cannot trust accuracy. So we'll do a lecture about that in the coming weeks. All right, so this is a point where I like to do the machine learning pipeline, just to give you this big picture of everything and how all these algorithms that you'll see me talk about SVD, and you should understand, oh, we're kind of at this stage. Or I'm talking about the vector space model, oh, we're kind of at this stage. I have X and Y, oh, we're kind of at this stage, the algorithms, performance, and so on. All right, so this short PDF here, just with that one, example of the machine learning pipeline. Then these are the word problems that we covered before. So we are done with this module. Okay, so we have now moved through this module, and we've just completed this module on the machine learning pipeline and feature engineering. Are there any questions before I move on to the next topic? right? So the next topic then, and the next two topics that we're going to cover this week, as I said, which are kind of related, they're very geometric types of machine learning algorithms. You should be able to understand all of this, as the concept is very simple, and to implement it in Python from scratch, just using something like NumPy, that should be enough. So we're going to start with KNN, and just keep in mind, I didn't write it here, but I guess I could have written supervised learning and KNN versus unsupervised learning and K-means. Okay, so K-means is unsupervised learning, KNN is supervised learning. So what is the difference really? Simple. You have, in both cases, you have your X matrix and your Y vector. You have it. But the difference is that KNN has values in the Y vector, whereas unsupervised does not have any values on the y vector. So essentially, there is no Y vector. So KNN then has an X matrix and a Y vector, but unsupervised learning only has the X matrix. So there's nothing to correlate to, and instead, the learning has to happen based on just what is in X. And that's the difference. And so we will talk about that, obviously, and I have a simple example demo that should help you out. All right, so let's take a look at now at KNN, and this is called the K nearest neighbor algorithm. All right, as you can see here, I have several things, so I'll talk about that first. These Jupyter notebooks, these three, you can ignore if you'd like, and instead just go to this link that says code. So that's where the same Jupyter notebooks are. So that it's on GitHub essentially. And so the GitHub will have several pieces of several scripts, several pieces of code that we're going to go through today that are going to be very helpful. And we'll use, most likely, the same iris data set, Fisher's iris flower data set that we use in Weka. Now we're going to use it for the KNN algorithm. So yeah, so this is the code essentially. I'll go over these notes today. And then the last thing that I want to recommend is this link here that says reading. I highly recommend that you start reading through this. So this talks about KNN, but also it has a lot of other topics that we will be covering this semester. So this is kind of like a blog post type of reading, and I recommend that you go through it. So it's traditional machine learning. So this talks about traditional machine learning topics. If you notice, in the little drawing here is actually talking about KNN. Hope right now you may not understand this, or maybe you do. This is something you learn in high school. And so a year ago, this is something that you guys probably learned in high school. How to sum the square of triangles. There's like a theorem about it by Pythagoras. But actually, you might be surprised that the whole KNN algorithm is based on this idea from thousands of years ago, right? So 1,000, 2,000 years ago. So anyway, so that's kind of the motivation. And so go through the reading, read through the notes. This talks a lot about a lot of the traditional machine learning algorithms. It also provides some notes on the things that I will be doing. So, I'll demo the code and I'll show you guys how it works. But if you want some additional notes, you can read through it. It'll explain that we use libraries. It'll again explain that we have classification and regression models. These are the classification metrics. These are the regression metrics. It'll show you how to bring in a lot of the libraries, how to split the data. Remember, we were splitting the data into 80 and 20%. So we'll be doing that again, but I'll demonstrate that today. There will be some introduction to a library called sklearn that actually, so most of the time we will look at doing the algorithms from scratch, but some of the times we're just going to use the algorithms from a library. So we don't have to code it from scratch. It'll just, depend. And so this provides notes on that. For those of you that don't remember object-oriented programming, read through this. This will become very useful later. As you know, in machine learning, you do want to use object-oriented programming. It just does everything simpler. It simplifies pretty much everything that we're doing. Performance evaluation, as I said, we'll cover these, but these are some of the functions that we will see. Some of the functions for the performance metrics. This we'll see today. This is a lecture that's coming up, and this shows you the equations on how to compute precision, recall, F measure, and so on. So we shall see that in the future. I'll give you a function for plotting performance. So you can see that. This topic talks about optimization, which is essentially what you are doing. Machine learning is all about this idea of optimization. You think, you look at your day and you want to know what activities you should do and what sequence so that you can accomplish the most with, and be effective at it. So that's optimization. And here we just have a set of algorithms in machine learning, artificial intelligence, that are trying to optimize parameters to get the best results. So definitely start reading through this also. It'll help you out. We'll talk about the chain rule later in the semester also, but this should be good. These are examples of using sklearn for the different algorithms. You can see there's the multi-layer perceptron, kind of like the one we did with Weka. So we'll cover this in a few weeks. And then you can see here, this is the algorithm I'm covering today, KNN, the K nearest neighbor algorithm. Here's the code that I will cover and discuss. The Euclidean distance, we'll talk about that. I've provided here some nice, I like history of machine learning and things like that, so I provided a little bit of a history on this Pythagoras, right? So the Greek philosophers, Pythagoras in particular, came up with this Pythagorean theorem. So this idea here, the theorem states, just to remind you, that given a triangle, the sum of the squares of the sum of the areas of the two squares on the legs A and B, in here A and B, right, equals the area of the square of the hypotenuse C in green. So square of this, the square of this equals that. And this is the famous equation, C square equals A square plus B square. So you can see that there. So I provided some notes, and we'll come back to this a little bit, but you can read through it. And that essential thing that you learn in high school is the whole idea for KNN. So we'll explore that. There's a few other algorithms here, like support vector machines, regression trees, and XGBoost, the t-test, etc., that are algorithms that are important. And so, start reading through this material, and I will provide, of course, more information later in the semester. All right, so that's for you to read. So I can close that. All right, so let's go back to table of contents now. Okay, so just laying out what we're doing. So this is your reading material. These scripts are essentially in this code. And then I have, these slides that I'll start with just to give some of the motivation. And then we can get into coding our first algorithm for machine learning. So let me start here, KNN presentation. I'm going to download this PowerPoint. Open it up. All right, there it is. So hopefully you guys can see it. Oops, yeah, you guys can see this, right? Okay. All right, so yeah, so some of the learning objectives with this example, student will learn about KNN. KNN is a traditional machine learning algorithm, simple algorithm and mechanism, right? So should be pretty straightforward. Here we have KNN. Not really optional for big data, not like massive amounts of data. Although some people have tried to implement this in like with parallel computing, but there are some parts that can be done like that, other parts that can't. But yeah, so it's good for quickly prototyping your data set. As we know, we have kind of two families, big data and traditional. So for big data, we're going to be using things like neural networks, deep learning. That means we have, gigabytes of data, 1 million rows or 1 million samples. Okay, and that's why we have Colab, for instance, and access to the GPU as I demoed at the beginning of the semester, so that we can do, handle data sets that are really large. Here, KNN, doesn't need, is still pretty good, and they're, not all data sets are huge. 10,000 rows, 100,000 rows, 100,000 samples is, something that KNN can easily handle. So some of the traditional algorithms, that are important, as I've mentioned, decision trees, like with XGBoost, that's an extremely powerful algorithm that's still very relevant. Okay. Some of you have, I think some of you may have not connected. All right. Yeah, so decision trees, a powerful algorithm is XGBoost. Naive Bayes will cover this in the upcoming weeks, and today we're looking at KNN. But just keep in mind, there is this classification. All right, so what is the vector space model, right? So this is the first thing that we're going to think about. So we all know that we live in three-dimensional space. We all know this, okay? So we live in three-dimensional space. And let me grab a pen here. So I usually do this with a pen. Okay, so this pen, if I just have like a little ant, that all this ant can do is move from here to here on this pen, like in just in that direction, that's a one-dimensional space. But if I have two pens, right? I need a second pen. If I have two pens, and I put them like in 90 degrees like this, so you guys can see that, then now they create like a sheet. And so that sheet is a plane, right? A plane of paper. And now the ant can live on the page, like anywhere. It can move, right? Because it's like a point. The ant is a point, so it can move anywhere on here because there are two axes of the page. You can see the pen there and there. So they create an axis. And if I have then 1, 2, 3, so for instance, I have this two-dimensional, and I add a third with the pen, now it's three-dimensional. So essentially I have this Rubik's Cube, right? And so this is a three-dimensional space. Now the point lives inside this Rubik's Cube, and it's got three dimensions. It can go in that direction, and this direction. So this is actually what you're seeing here in this graphic. So I have 1, 2, 3. So the key thing is you have to make some assumptions, but the key intuition is that you represent every point to be a sample. And then every sample has features. And those features describe some property of the sample. So here, for instance, we can see we have X, Y, and Z. So this is a three-dimensional space. So points for this are vectors of size 3, where in theory, you want F1, F2, and F3 to be independent of each other. That term is mathematically is called orthogonal, or as you remember from geometry, is a 90 degree, right? Either way, it just means that they're independent. So for instance, height and age, especially for children, are correlated, right? So a toddler at 1 year old is going to be like 2 feet, and then a kid at 8 years old is going to be 4 feet or something like that. So they are correlated, one to the other. So, but that doesn't meet the property of being uncorrelated. However, you can still use those two pieces of information. They're just correlated to each other. So we do have other techniques later on, like PCA, compression, etc., to make those two features really into one, because you probably don't need both of them because they're highly correlated. But anyway, the idea being that once you have variables that are uncorrelated, you have just enough information to represent that sample. And remember, a sample is always a point. In the Rubik's Cube here, it lives only inside here, and it's a point of 3 dimensions, okay? If I had just a sheet of paper, then, and we'll see this, hopefully this week with these ideas, if it's a sheet of paper, a point that lives here only is represented by a vector of size 2 dimensions, right? Sometimes we're going to call that R2, R3, and so on. So the question that you might have in your mind is, okay, you're saying that samples are represented, by vectors of a specific size, 2 or 3, and I can understand that. But what about iris? Fisher's iris, I remember, had feature 1, feature 2, feature 3, feature 4, right? Sepal length, sepal width, petal length, petal width. So that one has 4, not 3. So in that case, what happens? Well, the issue is that humans, us, people, we cannot really see anything, like conceptualize anything. It's a limitation of our brain that we can't conceptualize anything in higher dimensions than 3. We live in a 3-dimensional space. But mathematically, there's no problem with that. So mathematically, we can represent things as having 4 features, which essentially means that they are a point in a 4-dimensional space. Although we cannot visualize it, there would be some kind of a additional axis to the 3 dimensions, and that would be orthogonal. That is to say that it would have 90 degrees to all the other 3s. Like these have 90 degrees to each other. And so mathematically, that's totally doable. And we can scale that. If we have a vector that's size 40, that's fine. That means we have 40 dimensions in our space. And so all the math holds. Even if that's complicated for you to understand, you can always just think of it in 3 dimension. Think of the point in 3 dimension. Do your thinking there, and then just realize that mathematically, once you adapt it, it's still going to work the same way. Why is this important? Well, it's important, first of all, because what if I have 2 points in this vector space? Then now I can calculate a distance between one point and the other point. That's a fundamental concept, right? So I have this property of geometry where points can be, down here, they can be up here, they can be anywhere. And if I have multiple points in here represented by these axes, then I can now do calculations between them. And that's the key thing for this type of algorithm called KNN or K-means, is to understand each point in relation to all the other points. Okay, so this is a pretty important concept. This is called the vector space model. So for instance, in the example of network intrusion detection systems, you have the packet, and the packet, we want to know if it's like goodware or badware, right? So that's the classification. So we are going to extract data from the packet to represent it, okay? And we represent it as these features, which are going to be these axes. So for instance, X, Y, and Z become F1, F2, and F3, where F1 could be number of bytes sent, F2 could be number of bytes received, F3 could be the source port, right, for each packet that we are collecting. Okay, so you can see then here, we have the packet. We represent it in the vector space model format, which is essentially, if you ever get confused, just think, we're just making a CSV. So we're just going to make it like iris. This is why we start with these data sets, in particular iris, because it always helps you then when you're trying to create a new problem to make it as similar as possible to Iris. All right, so then the KNN algorithm, is the model that we would use, and we use it to classify our data. So it's a classifier, a supervised learning algorithm, into either normal traffic or bad traffic. Here's the example then. As I said, with network intrusion, you have a packet, a network packet that has headers. There's your Ethernet header, your IP header, your TCP header, and a payload. So just, ignore the Ethernet header for now and the payload, and just focus on IP and TCP headers, which is the more intuitive part. And we know we can extract from these protocol, service, source port, destination port. And so those become the features. So S1 to S3, each one of those rows is a sample, in its simplest form, a packet. And then F1, F2, F3 here become the features that represent that packet. And also, they represent these axes in a vector space. So here we have F1, F2, F3, but probably all the way up to F20 or F40. And that means we would literally have a vector space of size 40, where we can calculate distances between points. So remember, this is really important, right? So if this goes from F1, F2, F3 to F40, that means S2 is a vector of size 40, 40 values, one for each axis. But when we represent it in a graphical way, it would just be a point, one single point in this 40-dimensional vector space. Unfortunately, humans, at least until now, have not been able to visualize a 40-dimensional space, but this would be great if someday, somehow, a trick is found that we can start to visualize those things. But that hasn't been achieved just yet. All right, so does that make sense, guys? This is a really important concept, the vector space model, and as you know, that's the X matrix. The Y vector is another space, really, but it's just indicating a label for the point. So these are the points, S1, S2, S3, of size, let's say F1, F2, F3, all the way to F40, and then we just know that each one of the samples has an associated class. So in this case, probably not attack, 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 not attack. And this is what makes this a supervised learning technique. Here we have further to elaborate on this one. Wait. What is this one? Oh, maybe. Yeah. All right, there we go. So in this one, you can see that I have the same idea, F1, F2, F3, but the dimensions represent the axes, right, on this vector space. So if it's only F1, F2, it's a two-dimensional space, very much like a sheet of paper, like I showed you. F1, F2, F3, very much like a Rubik's Cube like this. But F40, just imagine somehow, right, that this would be a vector of more dimensions. They meet the properties of having 90 degrees mathematically, and every sample is just a dot, one point in that vector space. So if I have 2 points, then I have a way of calculating the distance between the points. Okay? Now you can see in this example, for ease of use, I always end up just using 3 dimensions, but there can be more. So here, for instance, now F1, F2, F3 would be something like a protocol. So from 0 to 20, is it 6, is it whatever? Source port, is it port 22, port 80, port 443? Destination port, same thing, port 5000, whatever it is. And this is a very overly simplified explanation of this. There would be better approaches, like making each of these services a binary, essentially their own feature, but for now, don't worry about that. That's almost like a disclaimer that I have to give on this idea, but to keep it simple, you can understand this. And then the range would go from, there are about 65,000 port numbers. So for these, this would go from 0 to 65,000, 0 to 65,000. Let's say this goes from 0 to 100. Okay? All right, so that's the vector space model. Now comes KNN, which is just the algorithm. So I'm just going to, first of all, describe the algorithm. We will implement this. I would argue that KNN is the easiest algorithm to understand, and definitely the one we want to implement. So KNN, essentially, step one, convert data to a vector space, because we need every sample, including a packet or whatever it is, as a point in this space. So once we're there in this geometric space, then the idea is that we calculate a distance between your one sample called the x-test sample and all other points or samples in the space. So that is, let's say I have 1,000 points in this space, right? And each one has a label. All right? So then now I bring in a new point, and that point in that space, I measure this individual distance between that point and all 1,000 other points in there. So that I end up with an array or a list in Python of 1,000 distances. Do you see that? And then what I want to do is I want to know, it's called K nearest neighbor. I want to find what are the 5 closest points to this point. How do I do that? A simple ranking. You guys have done bubble sort and all kinds of sorting algorithms, so you know exactly what that is. So you rank it, and now you take the distances that are the shortest, look at the 5 top shortest distances, and then for those 5 points in the vector space, figure out the class that is assigned to them. Because you selected 5, you're not going to have a tie, right? It's an uneven number, and therefore you're going to have one that dominates. It's going to be maybe 3 to 2. That's not ideal, but that might be the case. Or maybe you have 4 to 1. That would be excellent. Or 5, right? So different kinds of possibilities. But that's the algorithm. So you sort the distance in ascending order once you calculate those distances, and then select the 5 closest samples. So this would be called KNN 5. That's why IBK, right? So it's called, K is the number. The K nearest neighbor is like saying the 5 nearest neighbors. So K is usually the number that we want, and then we just pick the majority class. That's essentially the algorithm. And so this is the algorithm that we're going to want to implement, essentially. All right, so we are done with these slides. We looked at KNN, a traditional machine learning algorithm. It's very easy to implement. We looked at the vector space model. It relies on that, and how to represent packets in this model. Okay. And we learned the basic mechanism of KNN, of the KNN algorithm. I will be now just talking about one more thing, which is the Euclidean distance, which is the thing that we use to calculate the distance. And then from there, we should be ready to implement the algorithm itself. All right? Are there any questions on this set of slides, guys? All right, I'm not hearing any questions. Let's go ahead and close these slides here. All right. Oh, yeah. Okay, so the next thing we're going to look at is I have this PDF here called Euclidean, right? And this ties in, this is also described, should be described well in the reading that I gave you, so just look up that reading. But I have like my notes here. So I'm going to open up Euclidean. All right, here we are. So you can read up. I'm not going to talk about the history or anything like that. I encourage you to read through that little history. Imagine, one thing about machine learning, right? So we have, we just had like ChatGPT in 2022, and we've had like GPUs since 2007, and all this data, and then neural networks. Really, the basic idea, as you will learn, came around in like the 1940s with something called a perceptron, and the math has been there since at least the 1940s, right? The solution, something called descent of gradients, I guess. But this algorithm, KNN, the foundation for it has existed for thousands of years, right? So it goes back to the Greeks, Pythagoras. Pythagoras was one of the Greek philosophers who came up with this idea. Then there was a gentleman named Euclid, and Euclid he's very famous because he was a mathematician who put together a lot of the math of that time. Like, he looked at a lot of the mathematics from different mathematicians, and he put together a book. I think the book is called Euclid's Mathematics, something like that. And that's why a lot of the things, over your schoolwork that you've done in the past, you always saw like Euclidean this and Euclidean that. And it's just something that was captured in his Euclidean mathematics. But really it goes back to Pythagoras and the Pythagoras theorem that I read to you at the beginning of the class. So Pythagoras just had this idea, right, of this idea of the triangles, okay? And so that's essential. Yeah, so I don't have that drawing, so let me go back to the notes. Right, and he had this drawing in his mind that we can calculate the hypotenuse with this equation. Like here, right? So we have this, and essentially this little drawing here. So this, just to kind of put this into context, right? So to simplify this, because if, I have used a two-dimensional space, R2. So this would be equivalent in my vector space lecture to just a sheet, right? So we only have X, one axis, and another axis. So two axes. So everything just lives in that page. So that's why every point, such as I have these points S1 and S2. So S1 is represented by P1 because it's the value on the P-axis, and Q1, the value on the Q-axis. And then the same goes for S2. S2 is represented by the points P2 on the P-axis and Q2 on the Q-axis. But we can also label these. What we want to know is he came up with this idea. These were just points, right? There were 2 points in the space, but then he came up with this idea that if these 2 points form a square triangle, then you have this equation, right? So then he just labeled the hypotenuse is C, and then the other 2 sides is A and B. So he just creates this C square is basically C times C is C square, which creates a rectangle, or a square, sorry, and this is another square and another square. So then he found this relationship that this was C square equal A square plus B square. And then you use the root here, and then you have C equal this equation here. And that's the solution. But what's key here is, if you think about it, S1 and S2 are 2 points. So in the context of machine learning, they're 2 samples. That's why I called it S. And they're represented by 2 features, P1, Q1, P2, Q2. So these are the 2 features that describe these samples. So these could be like source port, destination port, source port, destination port. So what's really great about this is, even though this formulation works in 2D, you can easily expand this to more dimensions, 3 dimensions, 4 dimensions, 5 dimensions, and I'll demonstrate to you guys how this works. But essentially, we knew that we had a vector space of points where the points were represented by features, the axes, and then Pythagoras came up with this idea of triangles, this theorem, right, that we mentioned, the theorem states that given a triangle, the sum of the areas of the two squares on the legs, A and B in green, equals the area of the square of the hypotenuse, C in green. So, and then that relationship can be rewritten to create an equation. So we'll create this equation from scratch in Python and NumPy, and you'll see that this can easily be done, but that's essentially the idea that he came up with. And then the rest is just the algorithm itself, but that's the key insight, okay? So this is the idea that he came up with. Now we can go back to my PDF, where I just kind of have a little extension to it. If you look over here, you can click on this PDF. All right, and now you can see it's the same thing, right? So this implies that this is a vector space of higher dimensions, but we have points in here, and we know that we're going to have the Pythagoras theorem, a squared plus b squared equals c squared. So the Euclidean distance then is just going to be, the Euclidean distance finds the distance between 2 points in a multi-dimensional space. So notice that if we have more dimensions, let's say this one has n dimensions, right? So it could be 20. So then each sample P and Q is represents, let's say P as P1, P2, P3 all the way to Pn. And Q is represented as Q1, Q2, Q3 all the way to Qn. And now each of these is just points in these higher dimensional spaces. So this is the same example as before, right? So we just want the same equation. So we take Q1 minus P1, right? And that difference is A. That difference is A, so that's squared. The same over here, we take Q2 minus P2, and that difference just gives us this little line here, B, what's in green. So that's B squared. And so now we can calculate C squared easily and measure the distance. All right. Now, if we have, that assumes for this example, the equation, you might say, okay, that's great for a two-dimensional space, right? But the problem is, what about higher dimensional spaces? Well, in higher dimensional spaces, you just extend that idea. So you assume, just like here we had P1, or we had Q1, P1, Q2, P2. That's each dimension. So if we had a third dimension, it would just be Q3, P3. If we had a fourth dimension, it's Q4, P4. And we just have to follow the same logic. And that's essentially it. So here, for instance, I have an example of P and Q. P is P1, P2, P3, all the way to Pn. Let's say 15 dimensions. Q is Q1, Q2, Q3, all the way to Qn, so 15 dimensions, right? Whatever data set, right? You know, the bicycle example that we did in class, if you remember, I think it had 12, I want to say 12 features, so that's similar. So now, to calculate the distance here, we just take P1 minus Q1 squared plus P2 minus Q2 squared, and then dot, dot, dot. This just implies, you know, we're not writing it, but it's assumed P3 minus Q3 squared, P4 minus Q4 squared, all the way to Pn minus Qn squared. And a simple way of rewriting this sometimes is to use this symbol, which means the sum, and this is like what you guys do when you do for loops, right? So it's the sum from 1 to n of pi minus qi squared. So if you notice, this index is common. 1, 2, n. So essentially, you're just saying repeat this in a sequence, add up the results, and there you have it. So that's how we calculate the distance, and this is something that we're going to do in a little bit in Python. All right, guys, are there any questions on this ideas before we move on to the implementation part? All right, perfect. Great. So it seems like you guys get it, and it's very nice because you never knew, right, that when you were in high school and you were learning this, that you were actually already learning machine learning. All right, so now let's go ahead and go back to our table of contents. Let's just see where we are. Okay, so KNN is there. This is our current module. As you can see, we have covered the slides. We have covered this PDF. These three files are essentially what's in this code, so you can just look at code. And I've given you this reading for you guys to take a look at. So our next step now is to go to code, and there's several scripts in there because we're going to learn several things. And that is, we'll take our time with this, no problem. Remember, you were given about 100 practice problems in Python and NumPy, and you've been practicing them. And you're going to see some of those ideas start to appear here. Okay, I'm going to use Colab also for this. We don't need a GPU for this one, but it's a good idea to get comfortable with Colab, given that in the future when you have job interviews and things like that, you're very likely to be given Colab as a tool for your in-job problems or interview problems. All right, so as you can see, a lot of the materials, this just takes me to the Machine Learning Foundations repo. This is 365, so as you can see here, course repo, where I usually post the materials. I sometimes, in a year, I may create a 2026 of the in-class problems, but these are essentially some of the ideas that we cover, right? So KNN 2025 and so on, which is our first one. There's Iris CSV for those of you that still don't have it. Maybe we're going to need this file today, and then there's a few other scripts that we can look at. So I'm going to go back, and then here I have listed out like by different algorithms, Bayes algorithms. Oops, I didn't mean to do it. Deploy to web. So as I said, one of the things, because you guys are very good at web development and things like that, we're going to look at how to deploy our models online and the internet so you can share them with anyone. There's at least two ways that we're going to do that, something called Fast API, and then also Onyx models. So we'll see. So Fast API will be one of the first homework assignments probably, maybe in a couple of weeks. I'm still thinking through that one. But you could use KNN with Fast API, like our approach here. So we'll talk about that later. And then there's a few other algorithms here: neural nets, reinforcement learning, SVD, some transfer learning. Here's K-means, one version of it. And then here's a few links that you can look at if you'd like. But anyway, so today's then... Oh, and I have some homework. Sometimes when the homework assignments are involved, I will provide links here for your help, to help you out. All right, so here, KNN, this is the link. So we look at it. There's going to be a few things that we're going to explore here. I don't have a README on here, it seems. Okay, and I'm not signed in right now. So. All right, let me just move this thing. Yeah, there we go. See if I can move it to another location. Okay, so now I wish I could. I've been trying to make this. I don't know how to make this like the default. Pin maybe? Let's try it. Oh, there we go. Yeah, so pin worked. Good, that's a lot. That was taking a lot of room. Yeah, so now we are ready to do some coding. So we're going to need Colab, of course. This is our KNN. There's several examples in here. I also have a script of the Euclidean distance, as you can see that here. So essentially there's KNN and metrics. This is important because this provides performance metrics. This is the Euclidean distance that I just described. This is KNN NumPy 1, 2, and 3, just several versions of it. And this is a main ML pipeline. So I'm going to click this one. Right. And you can see here, this is an example of the overall pipeline that we can follow, my main ML function. Right, so usually I'm going to have some libraries. You can see that there. Okay. So NumPy is going to be a prominent one, and sklearn is another one that we'll be using a lot. This function just performs accuracy, one of the metrics, like F measure, precision, recall, etc. So that's a metric that we can use. Then here, there's a couple of ways that we can get the iris dataset. So one way is just to use libraries, like this one. Okay, and we get iris. Then we're going to have an area where we actually do the KNN prediction, right? So that's the algorithm. And then finally, we print out the results. Okay, so let's take a look now that we have just a very basic, just quick, kind of very simple introduction. Let's go ahead and use Colab. I'm going to open up Colab here. And, if you remember, we're going to use new notebook there. Okay. And I'm going to close this. We are going to need data now. So you're going to need another thing, which is your Google Drive. So how do you do that? Google Drive. Okay, and you go to Google Drive, and you probably have to sign in. And if you're signed in with, I'm already signed in with my Gmail account. And so I have my Google Drive, close this, and I have my Colab. And this, for a lot of the work that we will do this semester, this is a nice approach. Your Colab is where you hold your files. So you're going to have like your iris CSV file is going to be here. So for instance, for me, I already have it, iris CSV. Okay. If you guys don't have it, you need to download it from the link that I showed. Click on New and then File Upload. Okay? And then you will upload the file here. And then once you have iris.csv there, then you are going to connect Google Drive to your Colab. Okay? So the way to do that is we need to go to, let's see this. I think this has changed a little. Here, I think it's this one. Yeah, here. So, okay, so this is the first one I clicked on. So this thing that looks like a folder, right? Click on that. And then there should be something that says Mount here. Mount. Do you see that? Mount Drive. So then you click on Mount Drive. And then it says something like permit this notebook to access your Google Drive. So you're going to say connect Google Drive. And then we need to give it a second. All right, perfect. And now you can see there's this thing called Drive. So then you can expand that. You can expand this one. And now you see you got all these. I have a lot of folders because, I use this for the courses. But you need to look for the file that you're going to use. So in this case, iris.csv. So I'm going to not right click. You see these three dots here? You click on the three dots, and then there should be copy path, because you need this so that you can find where your file is located from Colab. So if you notice, I did that. So that's essentially all I have to do is give that in Colab to my code, and it'll find that file. Okay, guys? So that's really important. Then I can just close this. Are there any questions on what I just did? Questions? All right, so let's go ahead and continue. Okay, so that's there. And so now I can close Google Drive, essentially. They're already connected. I'm only going to be using Iris today. And now we should be ready to start playing with this. So we're going to need some libraries. So I'm just going to copy these libraries here. So that's going to be NumPy, sklearn. From sklearn, we've got data sets, we've got this, and this function train test split is going to be very important to us. So I'm going to run this, and you can see I get a green check mark, and that indicates that everything worked well. If for some reason you're missing a library like NumPy, then you usually have to do pip install, the name of the library. So for instance, NumPy. Okay, so just keep that in mind. Colab has become very smart nowadays that it essentially does that for you kind of behind the scenes. Go ahead. Any question? No? All right. So yeah, so that's the example. Another way of bringing in the data is to do this, right? So sometimes we're going to have data sets that are available in modules. So for instance, sklearn has this datasets module, so we can load Iris directly. You can see I got a green check mark here. And then now I grab Iris data and Iris target, and becomes my usual X and Y as we have discussed. Okay. You guys have seen Iris already when you use Weka, so you know what it looks like, right? And so we want to get a feel for it. X. And you can see the data right there. It looks a lot like the data we had in 5, 3.5, 1.4.2. The data that we had I mean, it's the same data set, really, that we had in Weka. I also can print the Y. Notice that now we don't have the words setosa, virginica, and versicolor, because as I explained back then, machine learning algorithms, once we start at this level, require the labels or whatever that information is to be numbers. Okay? But they still represent the same, setosa, virginica, versicolor. All right? So this is another way of bringing in the data, or we will bring in the data from this path. I'll show you how to do that in a little bit. Either way is, perfectly fine. So, but yeah. So that's the example so far. And then we need to create some kind of a machine learning algorithm and measure performance. We'll do that in another script, but in this script, I'm just grabbing one. I'm going to do one more thing, which is do this. So let me try something here. Took a bit. One thing, these matrices have a property called shape. So this tells us this is 150, 4. So this is good. That tells us there's 150 samples, and each sample, which is a point, right, has 4 features representing it. What were the features? Petal length, petal width, sepal length, sepal width. But if you remember in Weka, we split the data into 80% for training, 20% for testing, so that we end up with an X train, Y train, and an X test, Y test. So now we have 4 sets. We will always have 4 sets, so because we have to evaluate performance for supervised learning. So and this is going to be a common approach that we will use all semester. From sklearn.model_selection, I can import this function, train test split, which will do that split. I just have to give it X and Y, which is this X and Y. And I'm going to say the test size is 0.20. So it's the 80-20% split. Random state, 42, that just whenever you want to always, the algorithm by default will randomize the data, the samples, the points. So, but if you always want to get the same randomization, you provide a random state, like with a number. That way, whenever you use that number, you get the same randomization. That's useful for like debugging whenever you're trying to figure something out. All right, and then that should return 4 sets. So we have them here. So now if I print xtrain.shape, you can see it is 120, 4 instead of 150, 4. This is really important because you can see now this is 80% of the 150 samples. If I do the same for xtest dot shape, should be 30, right? And you can see it's 30, 4. If I print ytrain dot shape, that should be what? Just 120 because it's only the labels, remember. And if I do ytest dot shape, that should be 30. And that's it. That's 30 samples there, as you can see. So that's my data sets. So this is a common approach, things we've done in Weka already. Any questions on any of this, guys? Hearing any questions? Let me add a few more cells here in Colab. All right, so now, so we've completed this for now. Let's move on to another script in the KNN folder. Let's take a look at, so we've looked at, I think I started here at the bottom actually, didn't I? So main ML, we went over this pipeline. Then I have KNN numpy 3, 2, and 1, so we can go through these. And finally, we're going to have this one of KNN and metrics. But before that, let's take a look at Euclidean here. All right, so this is the exact same thing that I showed to you the math of, right? The Euclidean distance, Pythagoras, all of that. So now we're going to make a simple implementation of the Euclidean distance, just because that's going to be at the heart of what we're going to be doing. It's like a little function. Remember, every sample is a vector of something in that space that is represented as a point. So essentially, we're going to have 2 points always, and we're going to take the difference, the distance, using that triangle's Pythagoras theorem. Okay, so let's go ahead and do that. First, let's start from like the main area, right? And then think about how we can work our way back. So here I have a point, And I need to add some cells here. So I have these 2 points, P and Q, and they're in a two-dimensional space. One is 2, 4. The other one is 12, 14, right? So on the axes. And so what I do is I give P and Q as 2 points to a function called Euclidean, and this function will print the distance between the 2 points. I'll repeat that later with another point, or set of points, which is going to be here, P and Q, the same 2, 4, but notice that Q is now 34, 150. Somehow you can see it's further away, right? That's the implication. So the distance between these 2 points should be bigger than the distance between these 2 points. That's hopefully what we will see. We need a metric for that. Okay. We need a metric for that, so let's go back and take a look at the Euclidean distance, a simple implementation of it, and let's discuss it. All right, so you can see here I'm defining a function, right, called Euclidean, which takes 2 values, P and Q. And then in here, I'm going to essentially try to write that equation, right? The sum of the individual differences of P and, so there's 2, so it's like I'm going to take the difference between 2 and 34, and then the difference between 4 and 150 and square it. So I have to write the algorithm for that. So first we add up the square differences. So this is going to be a for loop for I in range, length of P. It can be length of Q, it doesn't matter. So the length is 2, as we know, right? So that's essentially, if I take, for instance, here, the length of P, not the full. Oh, I didn't run it? Okay, yeah, sorry. Give me a second. And you can see the length of it is 2, so essentially it's going to go 0, 1. It's like in the list, in the array, is just grabbing 0 and 1. So that's essentially what's happening. All right, so for I in range, length of P, that's the 2. Then we have a variable, sum of squares, as it's called. Essentially, it's an accumulator, as you know. So it initially is 0, but it's being updated every iteration. And what do we add to it? We add the difference. So P0 minus Q0 squared, P1 minus Q1 squared, and so on. So we add those. Those are the square differences, which if we go back to our notes, might remember that the equation was in fact, there it is, the sum, in a loop of the squares of Pi minus Qi, right? So that's what we had said, and that's exactly what we have, Pi minus Qi in the list squared. So we add them together into some Q, and notice this algorithm works whether this is, I'll extend this to, this is only 2 features, 2 dimensions per point. It could be 10 and it still works beautifully, right? So it could be iris with 4 values. It could be 784 values from, like the MNIST images. It can be anything. And then once we have sum all of them, we just take the square root, which is, this is the way that you write square root mathematically, to the power of 0.5 or half. And you can see in our notes, that's this square root right there. And that's it. And so we can, that's a beautiful way of creating a distance function, thanks to Pythagoras, they call it Euclidean distance. And it's one of several distance metrics that's exist in vector space models. All right, so now I'm going to add this equation. So that is now functional. So now I take the distance, and you can see it's 14. I take this other distance, and you can see it's 149. So essentially, this value is telling me that these 2 points are closer to each other than these 2 points, and that's really important. Additionally, I can notice that I can use points in different dimensions, right? So as long as they are consistent, they both need to be in the same vector space. So for instance, here, I'm going to say, I'm going to keep, these numbers like 7, 9, so that's 4, 4, that's 5, 6, it's probably 7, I think. All right, so it's just 1, 2, 3, 4, 5, 6, 7, 8. Okay? So now over here, these are going to be higher, but still 8. That's 4, 5, 6, 7, and one more, 8. So you can see they need to be, the property is they need to be aligned. They need to have the same dimension. Okay, just like that. And so this should work just fine. I can even change this to be like PW, QW, and then this is PW, QW. And if I take the distance, E2, oh yeah, so this is just 2. Okay. And you can see it still gives me a distance. Just perfect, because what's key is every data set is going to have its own vector space. Iris would only have 4, right? So it would be half of this. So 4 values. Sepal length, petal width, and so on. There you go. This one has 4. That's a vector space of R4. But if I calculate the distance, boom, I get a distance. So that's the key. That's like key insight. If you understand this concept, it's going to help you a lot in understanding machine learning. So definitely always think of your data as being put into this, and this will motivate a lot of your intuition. And from there, then, as we start looking at neural networks, things like that, there are some geometric properties there as well. And so this idea doesn't go away. In fact, it gets more interesting. But definitely, please read all the materials that I've given you, all the notes. Look at these lectures. And if you still are having trouble understanding this concept, let me know. And we'll see what we can do, given that this is such an important concept that you really need to master. Okay? All right, so we've done this example. I'll remove some of these middle ones. Okay, great. So yeah, we went over the Euclidean distance function. That's this one over here. So we've completed that script. Kind of a little bit of a warm up there. That one used a for loop. I wanna make some point here. So this one I wrote this intentionally to use a for loop because this is how you guys have been trained to do coding and programming. However, I've mentioned a couple of times that using for loops like this kind of operation is very slow because you're doing this on the CPU. If you were doing this with 10 million samples, this would take a very long time. So this is why we have libraries such as Torch and NumPy. And that's why I gave you those 100 exercises. So the idea being that we are going to rewrite this Euclidean distance in another way that uses NumPy. You have to understand that we can, just like here, we have, a vector where we're comparing all the i's, right? So all the zeros, all the ones, or the twos, all the threes. With NumPy, we can make those comparisons in one shot, like in parallel, if you will. So all the ones at the same time as all the threes, at the same time as all the sevens, they all get computed at the same time. That's what NumPy does. That's it's called vector arithmetic. And so we're going to replace this for loop with something else. And you just kind of have to understand in your mind that all values are being computed in parallel at the same time. Right? But we will explore that. So the Euclidean distance function will change. And this is something that you just have to get used to. Okay? Once quantum computers show up, you guys will have to relearn how to do all this for the architecture of quantum computers. Otherwise, you'll become, not as effective. Today, you have to learn how to do this for GPUs, because otherwise you're just not as effective. The days of the CPU, as far as machine learning, are no longer. We still use CPU for certain steps, but they're just too slow for everything. All right, so we go back to KNN here. So we've covered the main ML one, we've covered the Euclidean distance, and now we have this KNN metrics, and we can start looking at the KNN algorithm itself. So we can start implementing it, and I will implement it in NumPy itself. Okay, so I'm going to do this. So we're going to have a new area. So let's take a look at NumPy 1. So you can see this is now getting into the basic ideas. So I'll kind of just go through it, kind of lay out the algorithm of how it's going to work, and then we're going to fill in all the details that we need. So let's just do it in completion here. So let's, complete version. So first, I need this NumPy library. I'm also going to use this other library called collections, and I'm going to use something that allows me to count things called a counter. This just makes the codes shorter. I could do this from scratch, of course. We're gonna look at the 5 closest points, so that's the k equal 5. All right. Notice that here's my Euclidean distance function. The same I did before, but notice there is no for loop anymore. There's still a v and a v1 and a v2 that are coming in. Those are the 2 points. And notice that all we do is we take the difference between v1 and v2. v1 is a vector, let's say of 4. v2 is a vector, let's say of 4. Instead of iterating and taking the difference between each cell, we just do it all together. So v1 minus v2 produces a new vector of size 4 with just the differences, the result of the differences. We square it. You can see that there. So every one of those differences is squared. Then we sum it with NumPy, and then we take the square root of it. That's exactly what I did before in the for loop, but notice that NumPy just does this much more efficiently now. And this is going to be the little trick in machine learning that you just have to learn, right? The things are done differently now. Okay, but that allows us to process this much faster. So I have a Euclidean distance function there. All right, now we're going to think about what we need. So here you can see I'm going to have my X train, Y train, right? And these are the variables that I brought in before when I did the train test split. Okay, so let's just think of that logic. And that's going to be, let's say, the number of samples, the features, etc., right, that we need. So we have to bring that in. And then we have to define the actual algorithm we're going to be using. So let's talk a little bit about this algorithm. We won't finish this today, so I'll continue this on Wednesday with you guys. But let's see how far we can get. We have a few minutes left. So let's think about the logic here. So I already gave you the overall algorithm in the slides, right? And so we're just going to talk about it. So if you remember in Weka was in a category of algorithms called lazy algorithms. And the reason for that is that you wouldn't train a model and then use it. Instead, there was no real training phase. Instead, you're just using the algorithm in KNN. So essentially what you do is you are going to have test samples, let's say 30 test samples. And you're going to compare each of those 30 test samples to all 120 training samples in real time. So here, that's why we have the 30 X test samples, vectors of size 4. We iterate through this and grab each one, and then we send that, each one of those, as a parameter to the function predict. Okay? And then print that result. The function predict then is this one here. It takes in that test X, that simple sample that we just got, and it's going to compare it to all 120. So now we need to grab all 120. Notice that we grab those from here for X in X train. So these are the 120 vectors of 4 for iris. And so we calculate distances between test X and all data samples in X train in this case. So notice that not only we're using a list comprehension here, we iterate, grab all X train samples, 120 of it, each of the 120, and we pass that X and test X as two parameters into our Euclidean distance. So essentially as 2 points. So we're comparing our current test point with all 120 training points. Okay? So, and what this is going to do is this is going to create a list comprehension, a list essentially of all the distances. That's why this is called distances. So distances is going to become a vector of, this should be 120 actually, not 30. Because you're comparing one test sample to all 120 samples. So distances is a vector of 120 distances. That's going to look something like this. A whole bunch of distances, like the ones you saw me demo before. The next step in KNN is we're going to take these distances and we are actually going to sort them based on, from in ascending order, from the shortest distances to the highest distances. We really just care for the shortest distances. However, we have to do a trick. We want to sort them by distance, but we don't want the distance itself as a result. We want the index, because the index is going to tell us which of the 120 was the shortest, the closest, so that we can use that index to grab the corresponding label. Okay? So we will see this on Thursday. I'll print out the results, but keep that in mind. So we're going to use from NumPy this function called argsort. We're going to pass distances to it. And notice you should recognize that this is called slicing. I'm just slicing from 0 to 5. The 5 closest once I have sorted the data in ascending order. So we sort by distance and return the k closest neighbors. Argsort returns the indices of the k nearest neighbors, not the actual value. It uses the value, but it returns the indices. And the beauty of this is that, we would have to code that, but argsort does that for us with one line. So now we will have the indices of the closest points. And so now we can use those indices. If we have an array from 0 to 120, we know that it's index 3 and index 17 and index 55. Those were the closest. So those indices is what we grab. So they're like in a list, we iterate through that list. And then from the matching Y train, because remember we have X train which has 120 samples and Y train has 120 samples. So we, by index, grab the label, which is going to be in Y train, and now we have the labels, and that's something like getting something like 1, 1, 1, 0, 1. So we know, the type of, this is the class, actually, that we're looking at, and then this line here just essentially says, okay, the common label there is 1, and it returns it, and that's it. That's KNN, okay? All right, so it's 3:39. We'll stop at 3:40. I discussed the KNN algorithm, kind of like the overall idea. I strongly recommend that you guys try to go through these algorithms on your own until we meet again on Wednesday. And then on Wednesday, I'll pick up here essentially, and we're going to implement the entire KNN algorithm, reading the data from the CSV, and all of that. All right, guys, I will stop the video here.